So we're
Okay.
very happy to welcome Geoff back to Princeton. And he was telling us about leading order corrections to the QES prescription.
Okay. Well, yeah, thank you very much for inviting me to talk. So yeah, this talk's going to be on a paper that came out over the summer with Chris Akers, called the same thing as the talk. It's a paper that ended up being rather long and having a lot of content in it. So this is going to be sort of an overview of all the different things that we talk about. I encourage you to if you care about the details of anything, to look at the paper or to ask questions, obviously. Okay, so very boring first slide. We have ADS CFT, one in the 90s, came up with it, obviously. And one of the big things we've been trying to do in physics ever since is to understand what the dictionary is that relates the two sides of the duality. Okay. In particular, there's this one super important entry in the dictionary that in its first form, called the Ryutaki-Nagy formula. And it says that if you look at some reduced boundary state on some boundary subregion, then its entanglement entropy is given by the area of the smallest surface in the bulk that's sort of anchored on that boundary region. Okay. Of course, we've learned since through work by Faulkner, Lukovic, Mauder Sr., and then Engelhardt and Wall, that this formula needs quantum corrections, like many formulas. And so rather than having the area in here, we should really have the area over 4G plus the quantum correction, which is just the bulk entanglement entropy across the surface, so between the stuff on either side of the surface. So say if this blue fish is entangled with this blue fish, then that entanglement entropy contributes to the entanglement entropy of the boundary. And really, the formula I've given is just for static spacetimes. Really, there should be an extremization rather than a minimization, but don't worry too much about that because it won't play a major role in this talk. Okay, so this formula can be derived using some beautiful tricks that have been developed over the years from the gravitational path integral, which is sort of our most reliable source of information on quantum gravity. And it's led to a number of successes, including, of course, over the course of 2019, a derivation of the Page curve for an evaporating black hole. But that's all just very preliminaries, because what I'm going to be talking about this talk is the fact that if you just like naively apply the quantum extremal surface prescription to any state you get given without thinking at all about what you're doing, then you get paradoxical results. It doesn't make sense. In fact, these paradoxes already exist at order 1 over Newton's constant, G Newton. So they're leading order effects. You can't just imagine that the QES prescription is basically right, but there's tiny corrections that have to fix it. So this is really a big thing that needs to change. Paradoxes can be seen in all sorts of situations. They can be seen in calculations involving evaporating black holes, since that's the fashionable thing to do with quantum extremal surfaces these days. But they can also be seen in states that don't involve any black holes at all. So they're pretty general phenomenon. They do require a large amount of a leading order amount of bulk entropy. So you need some source of that. Fortunately, it turns out when you do more careful entropy calculations using the replica trick, then you get self-consistent results. You don't get these paradoxes. But what you see is that the certain assumptions that needed to be made in the derivation of the QES prescription, which is Lukovic, Mauder Sr., and then developments from there, fails. And those assumptions don't work even if you're just trying to get the leading order answer. And it's kind of unclear why they fail, actually, but we'll see that later. And so what you find is that instead, the naive QES prescription is no longer valid. Instead, it needs to be replaced by a more refined version. This refined version is defined in terms of smooth minim max entropies that are concepts from Oneshot quantum Shannon theory, a subfield of quantum information theory that cares about information, but information in a single copy of a quantum state. So ADS CFT obviously involves a single copy of a quantum state, so that's maybe not too surprising. But yeah, it's the right thing to be showing up really rather than von Neumann entropies. So that's reasonably satisfying. So yeah, and this connection to Oneshot quantum Shannon theory goes deeper than just the same quantities showing up. It turns out all the results in this talk, particularly the consequences they have for entanglement wedge reconstruction and the subregion duality, are very closely related to a particular task in one-shot quantum Shannon theory called one-shot quantum state merging. So I'll talk briefly about that towards the end of the talk. Okay, but let's start from the very beginning. We're just laying out why we have a problem with naive QES. Okay, and the situation I'm going to demonstrate this in is going to be what's called a dust bowl in ADS3. So we're going to consider ADS3 CFT2, and we're going to consider a boundary region consisting of this bit at the top and the bit at the bottom. So it consists of two intervals. Okay, so there are then two extremal surfaces which have different topologies. So there's this solid one going vertically and the dashed one going horizontally, but they both are homologous to the boundary region. So they're both sort of allowed RT or QES surfaces. Now that's true in vacuum ADS3, but it can also be true if we add some matter, this blob here sitting in the middle of the bulk. In particular, we're going to add a sort of order epsilon over G Newton amount of matter. So because of the G Newton in Einstein's equation, this is going to create an order epsilon amount of back reaction on the geometry. Epsilon will take to be order 1, but small. So the sort of back reactor geometry is very similar to the vacuum ADS3, and we still have the same sort of two surface setup. Okay, so if this matter is in a thermal state, it will have a von Neumann entropy, and in fact, its von Neumann entropy will have the same scaling as the energy. It will also be order epsilon over G Newton. Now what we can imagine doing is we can choose, by choosing our region B to be sort of half the boundary plus some order epsilon extra amount, we can set things up so that the area of this solid surface, called A1, smaller than the area of the dashed surfaces, A2, but that in turn, or that over 4G Newton is in turn smaller than the area of the solid surfaces over 4G Newton plus this extra entropy of the stuff in the middle. Okay, if the stuff in the middle is in a thermal state. Okay, so we're now going to consider a few different possible bulk states with this same boundary region, and we're going to see what the QES prescription gives in each case. So the first possibility is we're just going to assume that the matter is just sitting in some pure state. Okay, maybe it's energy eigenstate or something like that. So it has this geometry, it has the back reaction there, but fundamentally it's in a pure state, there's no entropy from it. So in this case, there's no contribution to the von Neumann entropy. This solid surface has a smaller entropy. So the von Neumann entropy of boundary region B is just going to be given by A1 over 4G Newton. Our second state we're going to consider is instead going to be a thermal state. So now we have all this thermal entropy sitting in the middle. By construction, okay, that adds to the entropy of this solid surface, the generalized entropy of this solid surface, but not to the generalized entropy of this dashed surface because it's outside the entanglement wedge of the dashed surface. And so that means there's a transition, the new quantum extremal surface to the dashed surface, and we find that the entropy is now A2 over 4G Newton. Okay, so far, no problem. This is just the QES prescription giving us sensible answers. But now we're going to consider a third state. And this third state is just going to be a mixture of the pure state and the thermal state. Some probability P of being pure, probability 1 minus P of being thermal. We'll assume they're both sort of order 1 quantities. Okay, so let's apply the QES prescription. Well, the generalized entropy of this dashed surface is still just A2 over 4G. There's still no contribution from quantum corrections. Now the area of the generalized entropy of the solid surface is A1 over 4G plus the entropy of this mixture of the pure state and the thermal state. Okay, up to a small correction, that's just 1 minus P times the thermal entropy, S. Okay, it's just the probability of it being thermal times the entropy if it was thermal. And so we get this answer that it's the smaller of A1 plus 1 minus P times S and A2. Okay. But there's another thing we know about this mixture of the pure state and the thermal state. It's that, the bulk state is just a mixture of the two. And because the map from bulk to boundary is linear, that means the boundary state is a mixture of the two. And in turn, taking a partial trace is a linear thing. So the reduced state on big B is also just a mixture of the two reduced states. And if I take a mixture of two states, then very standard bounds on the entropy of that mixture mean that the entropy of the mixture is just P times the entropy of the first thing, so A1, plus 1 minus P times A2, plus at most some order 1 correction. Okay. And now we can just compare these two formulas, sort of what we know it has to be given our answers up here and the answer we got from QES. And we see that for generic values of P, these things are just going to differ at leading order, right? In particular, if we make P relatively big, we can make this thing be minimized by A2. So it's just equal to A2. But this actual answer is still a weighted average of A1 and A2. Okay, so these are very different things. Okay, so as I say, you can also see the same paradox for an evaporating black hole. I'm just going to very briefly say how it shows up there, just to see the connection. So as we sort of all know by this point, if you look at an evaporating black hole after the page time, then in the semi-classical description, all the Hawking radiation is just in some thermal state. But magically, the QES prescription knows that there's some quantum extremal surface sitting near the horizon of the black hole up here. And the generalized entropy of that surface is the Bekenstein-Hawking entropy of the black hole. And so we find that the entanglement entropy of the radiation starts going down after the page time, consistent with unitarity. Okay, so that all worked out great. But now what we're going to do is we're going to take that state, and with probability P, we're going to measure it so that it gets projected into some pure state, whatever that might be. Okay, maybe we do a measurement in product basis or something like that. And with probability 1 minus P, we just do nothing and leave the state unchanged. So the semi-classical description now has probability P of this being pure and 1 minus P of it being thermal. Okay, so the QES prescription says, there's two possible extremal surfaces. There's an empty one, which has generalized entropy 1 minus P times the semi-classical entropy. And there's this one at the horizon, which still has generalized entropy equal to the Bekenstein-Hawking entropy of the black hole. Okay. But by exactly the same arguments as the previous slide, if we do unitarity, we've done this measurement, it has to be a mixture, it has to be a mixture of having done the measurement and got a pure state and not having done it and still have entropy equal to the Bekenstein-Hawking entropy. So it should just be 1 minus P times the Bekenstein-Hawking entropy. Again, these two formulas from QES and from self-consistency disagree at leading order. Okay, and in fact, if we make P relatively big, so P relatively small, no, P relatively big, get that right, then the QES prescription is going to give 1 minus P times the semi-classical entropy. This QES prescription is just going to give the semi-classical Hawking answer. It's going to be just as wrong as we would have been back in the 1970s. Okay, and the real answer is still 1 minus P times the Bekenstein-Hawking entropy. Okay, so that's very first part of the talk. Why we have a problem, or what is the problem? Okay, the second part is going to be why is there a problem? What was special about that mixture of the pure and the mixed state that meant that the QES prescription failed for them but gave sensible answers for the pure state and the thermal state individually? Okay. So if you have some thermal state that has a large number of pretty independent, weakly interacting degrees of freedom, then it's a fact that basically follows from the law of large numbers that we can find a very good approximation to that thermal density matrix by a state whose rank is just sort of e to the s, where s is the entropy of the thermal state plus some subleading correction. Okay, so you can really think of sort of S as like the log of the number of degrees of freedom involved in describing that thermal state. Same thing's true for a pure state, right? A pure state can be approximated, or indeed is, a state with rank 1, and rank 1 is e to the 0, so it's e to the entropy of the pure state. However, if we have a mixture of the two, then it turns out that finding an approximation, the mixture of the two, needs to have basically as big a rank as an approximation of the thermal state itself. Okay, so if we have this rho tilde of the mixture as some approximation of the mixed state, and then we just subtract off P times the pure state, which just has rank 1, divide the whole thing by 1 over 1 minus P, then we find an approximation to the thermal state whose error is bigger by a factor of at most 1 over 1 minus P. Okay, so we've used our approximation for the mixture to make an approximation of the thermal state. So the sort of required rank to approximate the mixture of the two has to be as big as the required rank to approximate the thermal state. But that's much, much bigger than e to the s of the mixture, right? Because the s of the mixture is just 1 minus P times the s of the thermal state. Okay? So as a general rule, these sort of large corrections to the QES prescription are going to show up when your bulk state has this sort of incompressibility property. So where the number of degrees of freedom required to encode your bulk state is much, much larger than just e to the s. So the real thing that's going to be involved is going to be the number of degrees of freedom that you need to describe the bulk state, not the entropy of the bulk state. Okay. This is sort of vaguely reasonable with given our intuition about how ADS-CFT works. It's sort of a quantum error correcting code, back to Ahmed and Qidong and Dan Harley. Okay, so we can be a bit more formal about this. We can be more formal using these quantities from one-shot quantum Shannon theory. So in particular, roughly speaking, this is the original definition actually, but the definition has since changed very slightly. The smooth max entropy of a state rho is just by definition the log of the rank of the sort of smallest rank state rho tilde that's still epsilon close to rho. Okay, so this is rather than just you saying that for thermal states the smallest approximation we can make has rank e to the s. By definition, for any state, the sort of smallest rank approximation we can find is e to the h epsilon max, okay, where epsilon is controlling the quality of the approximation. So this is really the thing that counts how many degrees of freedom we need to describe the state, characterizes the sort of minimum size Hilbert space that we can compress the state into and still get it back at the end with error epsilon. Another definition of it that's pretty equivalent is that the von Neumann entropy is telling us the expectation of the log of a randomly chosen eigenvalue of the density matrix, right? It's the sum over minus lambda log lambda, right? The lambda are the eigenvalues. It's the expectation with a distribution given by lambda of log lambda. This smooth max entropy is saying if I pick a random eigenvalue of rho, again from the distribution lambda, what's a lower confidence bound on its size? So how can I be confident that the smallest, that the eigenvalue that I pick will be bigger than 2 to the minus h epsilon max? Okay, that's a lower confidence bound on its size. This motivates very naturally.
Could I ask a question? So if epsilon is sufficiently small, is h epsilon just given by log rank rho, or?
Yeah, so if you
smaller, I mean, are there situations where it's smaller for any epsilon?
Yeah, so if you hold the state fixed and take the limit as epsilon goes to 0, then you'll recover h max, which is just log of the rank of the state. If you make epsilon smaller than the sort of smallest eigenvalue of the state, of course, rho may have infinite rank, right? If it's some thermal state on a infinite Hilbert space or something. So in that case, as you make epsilon smaller and smaller, this will just get bigger and bigger. So it's going to be important in this story that we're going to take epsilon to be maybe polynomially small in G Newton, but not exponentially small in G Newton. That's what you should have in mind. Or even in certain circumstances, we want it to be like order 1, but small, depending on. But yeah, we generally want to assume that this thing doesn't care too much about. Is roughly independent of epsilon. We want to assume that and that will be true for certainly things like thermal states where it gets dominated by a sort of range of eigenvalues with like a very small tail going away from that. Does that answer your question?
Yes, thank you very much. Yeah.
Great. Okay, so the smooth min entropy is just defined as sort of, you take the log of the largest eigenvalue for the approximation to rho that has the smallest, largest eigenvalue. Okay, so it's a upper confidence bound on a randomly chosen eigenvalue of rho. Okay, so these two things are sort of complementary quantities that together characterize the range of eigenvalues that are relevant to rho. Okay, when you only care up to some tolerance epsilon. Turns out there also exist conditional versions of these smooth min and max entropies. They'll play an important role in this talk, but I'm not going to give the definition because it's just a bit messy and unenlightening. You can look it up in the paper. But there's a very important point here, which is that for a von Neumann entropy, a conditional von Neumann entropy is just defined as the difference between the von Neumann entropy of AB minus the von Neumann entropy of just B on its own. Okay, for these smooth min and max entropies, that's no longer true. They no longer have this nice property that the conditional ones just difference between two non-conditional ones. That's going to play an important role. Okay, so now we've introduced these sort of new quantities, smooth min and max entropies. We can rephrase the statement from the previous slide as the statement that the QES prescription fails when these smooth entropies differ significantly from the von Neumann entropy of the state. Okay. And so that's what's going to happen. We're going to have to rephrase things in terms of these smooth entropies rather than von Neumann entropy. Okay, but before we sort of get onto that, what I want to do is just do a very explicit calculation that shows, for this simple example of a mixture of a pure state and a thermal state, how a more careful replica trick calculation gives you the right answer for the entropy and you don't run into any of these problems. And it's just a problem with QES, not a problem with, like, you know, fundamentally the way we calculate entropies in ADS-CFT. Okay, so how do you calculate entropies in ADS-CFT? What we do is we use this thing called the replica trick, which uses the fact that the von Neumann entropy S is determined by the limit of trace of rho to the n as n goes to 1. Okay, there's a few ways you can write the way it's determined by that. This is a nice one. But the key point is that if you can calculate trace of rho to the n for all integer values of n, and then somehow work out an analytic function that analytically continues that, then you'll be able to eventually work out the von Neumann entropy. So step one is just to calculate trace of rho to the n for integer n. Okay, so how do you do that? Well, you assume that your states, your bras and your kets are all prepared by Euclidean path integrals. Okay, so we have n rows here. Each contains a bra and a ket, or sums over bras and kets. So we have 2n sort of different Euclidean path integrals at this point in total. Now we need to do our partial trace because this row is like a reduced density matrix. And all that means is that you, sorry, my animations are completely terrible here. Okay, so the partial trace, I don't know what's happened there. This slide has got destroyed somehow. The partial trace means that you glue your bra boundary to the corresponding ket boundary. Okay, that's just a rule for how you do a partial trace in path integrals. So that's these blue lines. You take this complementary region, big B bar, in the ket, and you glue it to the corresponding bra, and you do that in each of the n bras and n kets. Okay, to calculate trace of rho to the n, we also have to glue together the parts of the boundary we want to keep, the B boundaries, but because we're calculating trace of rho to the n, not trace of rho to the n, we do so in a different way. We do so with the cyclic permutation that glues this first ket to this second bra, second ket to third bra, and so on all around in a big loop. Okay, and so that gives you some boundary path integral that's just, you know, closed geometry. It's just some number, and that number is trace of rho to the n once you normalize it. And finally, we're going to evaluate it using the bulk side of ADS-CFT. And so we do that by integrating over all bulk geometries that have those boundary conditions, or in practice, in the semi-classical limit, we just assume that that calculation is dominated by classical saddle points, and we sum over those classical saddle points. Okay, so that's all very standard stuff. But But unfortunately, turns out that in general, finding the bulk geometries with the correct boundary conditions for general n, finding all of them is very hard to do. So you need to make another simplifying assumption, just that you're going to consider what's called fixed area states, okay, which is some particular class of states that have this very nice property, where what happens is you've prepared some state using Euclidean path integral, and then you're going to measure the areas of all the extremal surfaces. So all these dashed lines just going to have their areas measured. Okay. So what does that mean? It means when you do the path integral and look for saddle points, you're no longer integrating over the area of that extremal surface because that's fixed by the measurement outcome. And so the saddle points are allowed to have conical singularities sitting at that extremal surface. In turn, that means your bulk geometries that show up for trace of rho to the n end up being exactly the same as the original bulk geometry, except that they have, like same as n copies of the original bulk geometry, except that they have branch cuts that sit at these extremal surfaces that permute the n sheets together in some complicated way. Okay, and this is allowed because it introduces conical singularities at these surfaces, but that's allowed because of the fact that we measure their area. Because this sort of geometry just looks like n copies of our original geometry for rho, turns out that the gravitational action cancels when you normalize these states. You divide through by trace of rho, except for the contributions that come from these actual conical singularities sitting at the surfaces, right? Because they don't appear in the normalization factor. So they just give this very simple contribution that looks like the conical excess times a over 8 pi g Newton. Okay, so what do these geometries actually look like? Be a bit more precise about them. Well, we know from our boundary conditions that, say, this big region B bar here got glued to the corresponding region B bar up here on the same sheet, right? So that means the part of the bulk that sort of neighbors that boundary region also needs to get glued to the same sheet. It can't be sort of glued to any other sheet. Wouldn't fit the boundary conditions. Similarly, in this region big B, the boundary gets glued to a sheet cyclically permuted round. I'm going to use tau to represent the cyclic permutation. It takes 1 to 2, 2 to 3, and so on. Okay, so in turn, that means that the part of the bulk nearest to that boundary region has to be glued to the cyclically permuted bra. Okay, but we also have this region sitting in the middle between the two extremal surfaces. And because we're allowed to have conical singularities sitting on these surfaces, and hence branch cuts, there's no constraint on what this part gets glued to. So it can actually get glued to sort of bra with like any permutation applied that we want. Since there's an allowed saddle for any permutation, then the sort of right thing to do is just to sum over all of those saddles corresponding to all of the permutations. You do that, it gives you a formula, looks something like this. This is the gravitational action from the conical singularities, and this is the quantum action of the bulk fields evaluating that background geometry. If we now said, okay, we're only going to consider the leading saddle in this thing, that leading saddle will always either be just the identity sitting here or like tau sitting here. And then we just take that answer just for that one saddle and analytically continue it. Then we get the naive quantum extremal surface prescription. Okay, so that's basically the Lukowitz-Maldacena derivation for these fixed area states. However, we know that that's the wrong answer. So we're going to try and avoid doing that. And instead, we're going to try and sort of keep all of these saddles, or at least all the relevant ones. And hopefully that will fix the problem and we'll get a more sensible answer. Hopefully that was the approximation that was the mistake. Okay, so it turns out we don't quite keep all of these saddles. And the reason for this is, so this C of pi here and this C of tau inverse pi, what I mean by that is I mean the number of cycles in the permutation pi and tau inverse composed with pi. Okay, the reason that shows up is it just controls the total conical excess of all the conical singularities of that surface. So we have these terms that look like C pi times A1 plus C tau inverse pi times A2. But A1 and A2 are formally infinite, right? As we go off out to the boundary, the area of the surface diverges. the difference between them is finite, but individually they're infinite. What that means is any saddle that doesn't maximize the sum of C of pi and C of tau inverse pi, it's going to be infinitely suppressed. We can just totally forget about it. That's not going to play any role. Turns out the permutations that remain when you get rid of the rest, like the ones that do maximize this sum, are associated with what's called non-crossing partitions of a disk. Okay, don't worry about what that is too much, but just know that's this is some set of permutations called non-crossing permutations that are well studied and have nice properties. Like they're things that mathematicians care about a lot. Okay, so now what we want to do is we want to take this sum over non-crossing permutations and we want to analytically continue it in n, okay, to non-integer values of n. The problem, of course, is that the number of terms in the sum is different for different integer values of n. When you try to go to non-integer values, then it doesn't make any sense. You can't just naively analytically continue the number of terms in the sum. Okay, so this seems a really hard challenge. Fortunately, as I say, mathematicians care a lot about these particular permutations, and there exists technology from the theory of free probability that lets us do exactly this thing, at least in the particularly simple case that we're caring about. I'm not going to go through in detail how that works, but basically it involves calculating this quantity called the resolvent, okay? So the resolvent is just a trace of the inverse of lambda minus rho, where lambda is just some complex number. And it's easy to see by Taylor expanding this thing that if you know all the sort of values of trace of rho to the n for integer values of n, then you can in principle work out the resolvent. Okay, it may be a hard challenge, it may not be possible in practice, but it doesn't involve any analytic continuation. However, in turn, if you know this resolvent, then what you can do is you can approach it, the real line, from above and below the real axis. And by looking at the imaginary part of the resolvent as you do so, then that will give you the eigenvalue density of rho. It will give you delta functions in principle at each of the eigenvalues of rho. Okay, so if we can work out this resolvent, we can work out the eigenvalues of rho, in turn we can work out the von Neumann entropy. Magically enough, for the particular mixture of a pure state and thermal state in a fixed area state that we were considering earlier, then you can use this technology for free probability to find a recursion relation that this resolvent satisfies. So if you want to see the details of how that works, it's in my paper with Chris. It's also basically the same trick is in the West Coast replica wormholes paper from last November. So this thing looks kind of horrible, but at the end of the day, it's just a cubic equation for R as a function of lambda, and cubic equations can be solved, right? Of course, no one ever got any insight out of directly solving a cubic equation using the general formula, so we're not going to do that. Instead, we're going to be physicists and make some approximations. And the first approximation we're going to notice is that as long as R isn't too big, then we have this huge term in the denominator here, very big term in the numerator here, and we can just ignore this entire correction. Okay? So you might say, well, maybe R gets really big and then that approximation wouldn't be valid. And that's true, it does. But if R gets really, really big, then this term becomes really, really big, and in fact becomes much bigger than this term. And so we can drop this term at really, really large R. And the key point is that because there's an extra e to the s in the denominator here, but not here, there's an overlapping range of R's in which both these approximations are valid. And so by using the two approximations, we can find overlapping regimes of validity, and we can solve for all values of R, and hence for all values of lambda, we can find R. If you make either approximation, you get a quadratic equation rather than a cubic equation. That's actually something that can be usefully solved. And in particular, you find that the solution for R has a non-zero imaginary part. i.e. corresponds to a non-zero eigenvalue density whenever the discriminant of the quadratic equation is negative. Okay, and that's just some simple equation in terms of lambda. Skip a few steps, let's look at the final answer. What you find is that you find two ranges of lambda where there's a non-zero eigenvalue density, where you have eigenvalues of this mixture, reduced state of the mixture. Okay, so the first one is here. It's at p times e to the minus a1. So these are the eigenvalues that come from the like pure part of the mixture, right? Remember, for the pure state, the entropy was a1, right? So most of the eigenvalues for that pure state would be e to the minus a1, but the probability of being in that pure state was only p, so that gives us the p times e to the minus a1. The rest of the eigenvalues are sitting way down here, okay? And so these eigenvalues are the eigenvalues that come from the sort of thermal part of the mixture. And so again, their eigenvalue is at 1 minus p times e to the minus a2. Okay, so the thermal eigenvalue is e to the minus a2, but probability of having them was only 1 minus p. So we have these two peaks. We can then very easily integrate to get the von Neumann entropy. And we find indeed that it's just p times a1 plus 1 minus p times a2 plus some small correction. Okay, so that was the answer way back at the start of the talk. That was the sort of sensible answer we needed to be true, but very definitely not the quantum extremal surface prescription answer. So by keeping all these other saddles, we've dramatically changed the final answer for the von Neumann entropy. Okay, so that's cool. We're sort of saved by the replica trick. The replica trick, you know, is still sensible even when QES isn't. But that's only some very particular situation where we just have a mixture of these two states, right? What we'd like to know is if the QES prescription isn't always right, then when is it right and what happens when it was wrong? Okay, so that's going to be my next part of the talk. So what's the answer to this? Well, the bad news is that even if we stick with fixed area states, then if we have sort of an arbitrary bulk state that has some complicated like tripartite entanglement between the three bulk regions, then the current tools, at least the ones that have made it over to the ADS-CFT literature, are not sufficient to explicitly do these replica trick calculations to find the resolvent and then find the von Neumann entropy. So that's annoying. You can find trace of rho to the n, you can find a formula for it, but you can't find the von Neumann entropy. However, there's a trick we can use. It's quite a nice trick. I'm quite fond of it. Which is that what we can note is that the formula you find for these fixed area states with arbitrary bulk state is exactly the same formula you would find if you evaluated the trace of rho to the n in a particularly simple random tensor network. So this random tensor network shown here. We take our little b prime part of the state, that's the region between the two surfaces. We plug it into some random tensor with output dimensions e to the a2 and e to the a1. And then we add in the degrees of freedom from little b to this side, apply some unitary, we call that the output big B, add in the degrees of freedom little b bar, like the stuff near big B bar, to this side, apply some unitary, call that big B bar. Okay, so this is sort of the obvious toy model, tensor network toy model you would make. Based on all our intuitions about the analogy between tensor networks and gravity. But what we're finding is that it's not just an analogy here, it's actually you get the same identical mathematical formula in both cases. What that means,
so
sorry, we can...
Could I ask a question? What's
yep.
here, T or U, or both?
T is random. U can be, but U is just a unitary. We're assuming this has sort of infinite output dimension. So applying this unitary here doesn't make any difference at all. We could have just said that B is this thing plus this thing. So the important randomness comes from T.
So what's the exact claim? So an average over T of what?
Yeah, it doesn't hugely matter as long as your bulk leg isn't too big. But the simplest one is just imagine that T is a tripartite Haar-random state. Well, you can either make T be a random isometry from this leg to these two legs, like a Haar-random isometry,
okay,
or
good.
you can make it be a just a tripartite random state on these three things that ends up being the same thing because this leg is so much smaller than
and
these
then
two.
you integrate over t.
Yeah, exactly. You calculate the expectation of trace rho to the n of that whole thing all over t.
Thanks.
Cool. Okay, so because we have these exact same mathematical formulas show up, if we can work out the expectation, if we can work out what the answer is for the tensor network, right? Even if we don't do it by doing the analytic continuation, even if we just use some other trick about how we know like matrices and tensor networks, random matrices work, then we can indirectly do the analytic continuation because we're working out what the answer must be. But that means because they're the same mathematical formulas, we're also doing the analytic continuation for gravity by doing something that's not an analytic continuation for a tensor network, by doing some other mathematical trick for finding the answer for a tensor network. So that's really cool. We're genuinely doing a gravity calculation, but we're doing it by just like plugging in some known results from quantum Shannon theory and quantum information theory about tensor networks or about random unitaries. Okay, so as I say, luckily enough for us, this tensor network answer is known. It's the sort of question, or very similar questions, are things that quantum information theorists care an awful lot about. And so we can just use that answer, and what we find is a refined set of conditions for when the QES prescription is valid. Okay, so to see what that is, refinement is, let's first state the sort of normal quantum extremal surface prescription in the following way. So there's two possible answers the extremal surface prescription can give. The first is the generalized entropy of surface gamma 1, okay, the solid surface in my old diagrams. So this is the area of that surface over 4G, plus the generalized entropy of everything between it and the boundary, right? So the stuff near the boundary region B, which we call little b, and the stuff in the sort of center of the bulk, which we call little b prime. And this is valid when it's smaller than the generalized entropy of the other surface, but we can equivalently state that as it being valid when the conditional von Neumann entropy of little b prime conditioned on little b is less than the difference between the two areas. Okay, that's just rewriting the condition that this thing is less than this thing. Okay, and equivalently, this one's true if it's the smaller of the two, i.e. the conditional von Neumann entropy is bigger than the area difference. Okay, so using our tensor network calculations, we can then find that at least for fixed area states, the more refined prescription is the following. You get the generalized entropy of surface gamma 1, not if this conditional von Neumann entropy is less than the area difference, but if the conditional smooth max entropy is less than the area difference. That's bigger in general than this von Neumann entropy, so this is a stricter condition for this to be true. Similarly, we get the generalized entropy of surface gamma 2 if the conditional smooth min entropy is bigger than the area difference. Okay, that's smaller than the von Neumann entropy, so again, it's the stricter condition. That means we have some intermediate range where the conditional smooth min entropy is smaller than the area difference, but the conditional smooth max entropy is bigger. Okay, and in that case, the general answer is just that it's complicated, and it seems like there's not some general simple rule like the QES prescription, but at least we know that the QES prescription is not right, and you should get like large corrections. Okay. So just to give you a bit of intuition for why this is the right thing to be showing up, we'll see later on in the talk that in a particular sense, this conditional smooth max entropy is the number of qubits needed to sort of explain the state on little b prime, or to communicate it to the state on little b prime to someone who already knows the state on little b. So this is like the region big B already knows everything on little b. It wants to try, the question whether it can find out the stuff on little b prime comes down to whether the amount of information needed to communicate that part of the state is less than the difference between the areas of the two surfaces. What about this condition at the bottom here? Well, that actually has a sort of pretty simple intuition for it, which is that for pure states, the conditional smooth min entropy of little b prime conditional little b is actually has necessarily equal by definition to minus the conditional smooth max entropy of little b prime conditional little b bar. So for a pure state, the conditional von Neumann entropy is, the conditional von Neumann entropy of little b prime conditional little b will be minus the conditional von Neumann entropy of this thing. In this case, it's min on one side and it's max on the other side. What that means is we can rewrite this thing as the conditional smooth max entropy of little b prime conditional little b bar being less than or equal to A1 minus A2 over 4G. Okay, that's just the same condition as this condition here, but for big B bar rather than for big B. So this is just by complementarity for pure states. By pure states having the same boundary entropy on the two complementary regions, then sort of this condition basically automatically implies this condition. Okay. So that's just some intuition for why we would expect it, but really it just comes out of the maths that this is true. But all that I've said so far, that the equivalence with tensor networks is very much only true for fixed area states. And in general, the states that we care about do not have fixed area. They have some semi-classical small fluctuations in the area. Unfortunately, for non-fixed area states, even just, as I said, even just finding the replica geometries for trace of rho to the n involves very complicated back reaction. It's we don't know how to find them explicitly in general. So again, we resort to using a trick. And that trick is that if we have a general semi-classical holographic state, then we can write it as a superposition over fixed area states, just like we can write an arbitrary state of a particle as a superposition over states of where the particle has fixed position. And in fact, if we only want the fixed area states to be fixed to some polynomial precision in G Newton, then the number of states in the superposition is also polynomial in G Newton. However, by similar arguments, the ones we saw about at the beginning about how an entropy of a mixture is sort of roughly the expectation over the entropies of the things in the mixture, then this actually implies that at leading order, the entropy of the semi-classical state, the boundary entropy of the semi-classical state, just the expectation of the entropies of the states, fixed area states in this superposition. Okay, since all the states have the same semi-classical geometry at leading order, this means that the sort of leading order entropies are the same for the semi-classical states as for the fixed area states. So that means that our rule for the refined QES rule that we introduced in the previous slide is also valid, at least at leading order for general semi-classical states. Okay, so there's a couple more things I want to talk about. It's going to be very brief sort of mention of them. I'm not going to have time to go into detail. There's going to be an informal chat this afternoon, I think, for IAS people. Happy to chat more about it then. And the first of them is how this connects to entanglement wedge reconstruction, this idea of quantum state merging. Okay, so very briefly, entanglement wedge reconstruction is just the idea that everything in between the sort of quantum extremal surface and the boundary, everything in the bulk in this sort of whole region, is actually secretly encoded in that boundary region. Okay, that's the sort of intuitive statement. You make more precise versions of that statement, and normally they involve something called a code subspace. In this paper, we actually introduced a more general definition of entanglement wedge reconstruction that generalizes that code subspace definition, that just says you consider an arbitrary bulk density matrix rho, and you consider some bulk operator that acts somewhere within the entanglement wedge, okay, for that particular state rho. Okay, so this is specific to the state rho. And then the claim is that we can find a boundary operator that acts only on region big B, whose action on a purification of rho is the same as the action of the bulk operator acting within the entanglement wedge. Okay, so if rho is a maximally mixed state on some code subspace, then this is just the usual definition that the boundary operator needs to act correctly on states in the code subspace. But by allowing rho to be arbitrary, we generalize it somewhat. We allow ourselves to take advantage of particular properties of rho. Like, we can take advantage of our expectations about the bulk state in order to do a better job of entanglement wedge reconstruction. So this is a bit more of a general definition. It's the right definition, I think.
But if rho is a pure state, it looks like this definition is.
Yeah. So if rho is a pure state, well, if rho is a pure state, then the bulk operator will presumably change that pure state to a different pure state, and so like it's a non-trivial thing still. Being able to do entanglement wedge reconstruction is like being able to do like completely state dependent. Like your operator only has to do the correct thing to a single state, but it's still non-trivial because it's only allowed to act on big B, right?
I know, but your condition for pure states seems too weak.
No, it's so we're still requiring that it takes. So it needs to take that pure state to the correct pure state. It's not that it just needs to have the correct expectation values. We're requiring it to have the correct action. I think that's the. If we were just requiring to have the correct expectation values, it would be trivial. You could just use something proportional to the identity. But if we require it to have the correct action, so take the correct starting state to the correct final state, then basically what this requires is it requires the two states have the same reduced density matrix on big B bar, right? If I say had something, if let's say this central region just wasn't in the entanglement wedge at all, right? And my bulk operator acts in the middle, then that will change the reduced state on big B bar, okay? And so there'll be no way to like do that, even just for that single pure state by just doing something on big B, just because we can't change. Yeah, there's a constraint that we require things to be unitary. Maybe that's what you're missing. Does that answer your question? If your bulk operator is unitary, your boundary operator also has to be unitary.
Okay, thank you.
Yeah, sorry, I should have said that earlier.
Could you explain how this is different from this idea of the code subspace? Because
yeah, it's just more general. So for example, yeah, if rho is maximally mixed on some code subspace, then it's basically the same. But maybe like rho has some large eigenvalues and some very, very small eigenvalues. And by this definition, you don't have to worry about the very, very small eigenvalues because there's only a tiny probability that it's one of those eigenvalues. Maybe rho has some particular entanglement between here and here, right, that you can maybe take advantage of to do your reconstruction. It's just a more general. You could say that you just don't include those degrees of freedom in the code subspace and get something kind of similar, but it just is a more general definition, right? Like,
isn't there some subspace here implicit in this definition of saying you take rho and you act with all the bulk operators you care, right? You will generate some subspace, and it has to work for that subspace, right?
Yeah,
maybe it's a subspace.
Yeah, it's a question of how you define the error to some degree. It's a question of whether you care about all states. Yeah, you can say, okay, that rho has some set of eigenstates and it needs to do the correct thing on them, or at least all the large ones of that large eigenvalues. But it's a question of whether you weight the error based on how large the eigenvalue is, or you treat all the states equally. And that can affect the answer.
In which case do you weigh by the eigenvalues?
In this case, we're weighting by the eigenvalues of rho. In the case where you just have a code subspace, you're treating all states in that subspace equally. That's the only sense in which it's more general, I think.
Okay.
But yeah, it agrees with the usual definition if you make rho have a flat spectrum. Okay. Oh, another thing is that like the eigenstates of rho might be entangled across the two regions. And normally with a code subspace, we want to say there's some code subspace for little b prime and a code subspace for little b and so on. So it's a bit more general in that way too. Anyway, turns out when you use this more general definition, and if you don't, but just use the right rho for your code subspace, you find that the condition for entanglement wedge reconstruction is exactly the same condition we just found for the QES prescription. Namely that, say, to be able to reconstruct the central region, we need the conditional smooth max entropy of everything in the central region to be less than the difference between the area of gamma 1 and the area of gamma 2. Okay. So now I want to briefly talk about the connection to one-shot state merging. So what is one-shot state merging? It's the following question. We assume that there's some pure state, psi ABR, okay, that's shared between Alice, Bob, and a reference system, someone else. Okay, and the aim of the game, so they know what the state is. Okay, they know that the state, Alice and Bob know the state is psi, but obviously, you know, it's entangled with the reference in general, so they can't just do whatever they want to it. The aim is going to be to transfer Alice's part of the state to Bob, while sending as few qubits from Alice to Bob as possible. Okay. So it turns out, the right way of thinking about it, this is just exactly the same as the task is exactly the same as the Schrodinger picture version of entanglement wedge reconstruction. So the way the analogy works, or the correspondence works, is that the part of the state Bob already has is like the bulk state in region little b, right? That's the bit he already knows how to decode. He doesn't have to worry about like what the areas of the extremal surfaces are. Alice's part of the state is the bulk state in region little b prime, the stuff in the center that Bob receives maybe some noisy information about, but maybe he doesn't necessarily learn everything. And then, yeah, the aim is to get Alice's part of the state over to Bob, i.e. to have region big B be able to construct this bulk state in region little b prime. Turns out the minimum number of qubits that you need to do one-shot quantum state merging is exactly this conditional smooth max entropy. The conditional smooth max entropy of Alice's part of the state, conditional Bob's part of the state. That's, of course, exactly the quantity that showed up in gravity. And in fact, the maximum number of qubits that you can learn about region little b prime from region big B is just the difference between the two areas, A2 and A1. Okay, this was discussed in a paper I wrote with Patrick Hayden a couple of years ago. I think other people have also discussed it. So gravity is seemingly saturating this lower bound on the number of qubits you need to do to transfer, need to have to transfer the information. However, there's a subtlety here, which is that when you do one-shot quantum state merging, it's crucial that you have what's called a classical side channel, that Alice is able to just phone up Bob and tell him some classical information over the phone about maybe outcomes of measurements she did on psi and stuff like that. If you don't have that, you need to send a lot more qubits. In gravity, of course, there's no classical side channel. Like there's no, the amount of classical information that can be learned about little b prime is actually just the same as the amount of quantum information that can be learned. There's no extra classical information. You can see this using a Halevo bound that was done by Bao and Aguri a couple of years ago. But what you do have is what's called a 0-bit side channel, in that what you're actually learning is not just A2 minus A1 qubits, but actually what Patrick Hayden and I called alpha bits for alpha A2 minus A1 over 4G divided by the sort of total amount of information that's sitting in region little b prime. And that, it turns out, is more useful than just being able to learn this many qubits about the region. And in fact, having these extra 0 bits turns out to be the minimum sufficient information to be able to do state merging with only this many qubits. So gravity is really being as efficient as it possibly can be about getting the information communicated through to the boundary region big B. Okay, so I'm pretty short on time. I only have 2 slides left. Just want to, yep.
When you say that there's a 0-bit side channel in this problem, if I understand correctly from your definitions, what that means is just that Bob can already decode small subspaces of B prime.
Yeah, it's what it really means. Like what it really is that instead of just having some qubits, we have some qubits. We actually have alpha bits of everything in the region. So what it means is rather than there's just like one e to the delta A dimensional subspace of little b prime that he can decode any e to the delta A dimensional subspace of little b prime. And being able to do that is more powerful than just being able to, more useful than just being able to decode one particular subspace. And it turns out that that's actually sufficient to the going from one particular to any subspace it gives you the same utility as being able to send classical information on the side. Does that answer your question?
Yes. But what is your statement? Third from the bottom on the slide, maximum number of qubits is A2 minus A1 over 4GN.
Yeah, if let's say the classical space-time is well defined, but I get to decide what the bulk state in it is. Okay. And so I can choose any bulk state I want, and then someone else is going to like get access to the reduced state on big B, and they're going to try and like learn the qubits that I encoded in my state, in the bulk state, right? But I was only allowed to encode things in little b prime. The sort of maximum number of qubits that we can send this way is given by the difference between the two areas over 4G.
Okay.
Okay, so the final thing I want to talk about is that sort of implicitly, so far in the talk, I just assumed that there were only two extremal surfaces that played an important role, right? And that we just had to compare the generalized entropy of the two of them and maybe some conditional smooth min-max entropies and stuff. But the two surfaces were the only relevant ones. Of course, for a general space-time, you can imagine arbitrarily complicated situations where you have loads and loads of different extremal surfaces. Maybe you have some complicated like wormhole structure or something. You can have arbitrarily complicated situations. So you want some definition that is just completely general. So we made such a definition that seems right based on tensor networks. But so far, we only have a definition for static states. So let me explain what that definition is. We first define what we call the max EW, or max entanglement wedge, as the largest region in the bulk, little b, that satisfies the proper following condition, that when we look at some subregion of it, little b prime, then the conditional smooth max entropy of everything outside the subregion, condition on the subregion, is less than the difference between the two areas. Okay, and we require that that be true to be the largest region such that that's true for all subregions. So I'll say in a minute, it turns out this is a well-defined thing to ask, even though it might not be obvious that it is. So this is going to be the region that is sort of fully reconstructible, fully encoded in the boundary region big B. It's the region that you can like definitely learn everything about, guaranteed from the boundary region big B. Then there's going to be another region we define called the min EW, which is going to be the smallest region. It's sort of going to be complementary to the max EW. It's bigger than the max EW, in fact. The min refers to min reconstructibility, not min size. So this is going to be the smallest region, little b, such that if we look at any chunk, any big little b prime bar that's like outside that region B, then the conditional smooth min entropy of that extra chunk condition on B is bigger than the area difference. Okay, so this is sort of, this is the region where nothing outside it has any influence on B at all. So this is the region that like some information might get through. This max EW is the region that all information gets through. Finally, if and only if these two entanglement wedges are equal to one another, then we call that the entanglement wedge. Okay, and otherwise we just say that there isn't a uniquely defined entanglement wedge. This is a change of the definition of the entanglement wedge, but I think it's the right one. Of course, as I say, at the moment, it's only all defined within a static slice. There's very preliminary work with me, Chris, Liz Waldenheim, student at Berkeley, and Adam Levine here, starting to try to think about how to generalize that, but we still have a very long way to go. Okay, so just to very briefly state some properties of these min and max EWs that are true and that you would need to be true, so encouraging signs. The first is that they're well-defined things. When I define things as like the largest wedge satisfying some property and the smallest wedge, then there actually is a unique largest wedge and smallest wedge, right? Wedges, there's like a partial order on wedges from one containing another, not a total order. So it's non-trivial, that's true, but it is using the properties of these smooth min and max entropies. Another property is that if we have a pure state, then the max CW is equal to the mini W of the complementary region. Again, this makes sense, right? If big B learns all the information about some region, then big B bar can't learn any information about it. Another property is that the max CW is always contained within the mini W, okay? This makes sense, right? Max CW is the region you learn that B learns everything about. Mini W is the region it learns some stuff about. One needs to be contained in the other. Another one is we look at two regions, look at B1 that's contained in some larger boundary region B2. Then the min and max CWs for B1 are contained respectively at the min and max CWs for B2. Okay, so increasing the size of the boundary region just gives you more information, not less information. It's called entanglement wedge nesting, or min max CW nesting. And the final property is that we said that when these two things were equal, we would call them the actual entanglement wedge, right? Turns out whenever that happens, then you can show that that is the surface of minimum generalized entropy. So in other words, whenever we're saying that the entanglement wedge is well defined, then its definition is exactly the same as the old definition of the entanglement wedge in terms of the minimal quantum extremal surface. So yeah, it's not that we're like correcting the definition of the entanglement wedge, we're just constraining the circumstances the way it's well defined and saying that otherwise all you have is a mini W and a maxi W. Okay, so that's all I have to say. Just end with some brief remarks, sort of takeaways, if you will. If you zoned out for this entire talk, here's what to vaguely remember from it. The first big thing is that the replica trick is really quite clever. It knows even more than the QES prescription does. The QES prescription is sort of magically clever. It even knows about the page curve, but the replica trick knows even more than that. So it really seems like the replica trick, knows everything you could possibly hope it to know. For the moment, we'll see. Another big takeaway is that from a quantum information point of view, it was always weird that holography involved von Neumann entropies for things like determining the entanglement wedge. And the reason for this is that operationally in quantum Shannon theory and so on, von Neumann entropies only play the most important role when you have a large number of copies of the same quantum state. You need a sort of law of large numbers to make the von Neumann entropy be the relevant thing. If you only have one copy, the important things are these smooth min and max entropies. So what we're saying is that reality, even in holography, was really always the smooth min and max entropies that were important. It's just we were often considering states that implicitly had some law of large numbers. They were thermal or something like that, and so we could get away with considering von Neumann entropies. Final comment is that there's a lot of leftover open questions from this. As I mentioned, like extending this sort of more general rule from more than two extremal surfaces to time-dependent spacetimes beyond the static case is something that we're still trying to work out how to do. Maybe it will require using the so-called maximum prescription. We don't really know at this point what the right thing is. Another comment is that we showed this refined QES prescription by sort of calculating trace rho to the n for integer values of n, and then calculating what the answer had to be for the analytic continuation by using the tensor networks. But we sort of didn't directly see, like just by looking at the mathematical function as a function of trace rho to the n, why sometimes dropping all the subleading saddles and making the Lukowitz-Maldacena approximation is completely fine and sensible and gives you this really nice right answer of the QES prescription, and why just mathematically sometimes the approximation completely breaks down when you analytically continue. And it's certainly true that analytic continuations and approximations play badly with one another, and so you have to be careful. But it would be nice to like just directly see the condition come out of the maths for like, okay, you can see here we can get away with it, and here we can't just by looking at the mathematical functions. And we don't have that yet. So that's another interesting open question. Okay, that's all I have. Thanks a lot. Any questions?
Thank you. Any questions, anybody?
I guess part of the problem for this, some of these last points would be solved if one understood the tensor networks a bit more generally, right? For situations.
Yeah, I mean, I think that's one of the, that's particularly this first question. One of the reasons I'm really interested in it is I think if we could answer it and work out what the right answer is, even if we just sort of have to guess it, it might give us some really big hints about like how to go beyond tensor networks to like having some model of like what the covariant, you know, the time, like the emergence of time in the bulk is, and what's going on with like the covariant part. And, you know, like maxi-min is obviously a hint, quantum extremal surfaces are a hint. But something, because these smooth min and max entropies satisfy pure nice properties, because the conditional ones aren't just the difference between things, the rule is going to have to be more complicated, and that means it might give us more information about, like, tell us more pragmatically like what's actually happening in a space-time. So I think that's one of the really interesting things about it to me. But yeah, as yet we don't know what the answer is. So yeah.
Well, last call. If there are no more questions, let's thank Geoff again for a beautiful talk. Thank you.
Okay.